Welcome! In this session, we'll explore the problem number 1529, bulb switcher 4. We'll walk through the problem, consider different approaches, and develop an efficient solution. Let's get started. The problem introduces a binary string called target, which consists only of the characters 0 and 1. Initially, all bulbs are turned off, which is represented by the string 0. You are given a switch that allows you to flip any prefix of the bulbs. This means that if you choose an index I, all bulbs from index 0 to I will have their states flipped. Flipping a bulb means changing its state. If it's 0, it becomes 1, and if it's 1, it becomes 0. The goal is to determine the minimum number of flips needed to transform the initial state of the bulbs into the target string. The input will be a binary string target, and the output will be an integer representing the minimum flips required. Let's look at an example to understand the problem better. Suppose the input target string is 10111. Initially, all bulbs are off, so the state is 00000. The first flip occurs at index 0, flipping all bulbs from index 0 to 0, resulting in the string 11111. Next, we flip at index 1, flipping all bulbs from index 0 to 1, which gives 10,000. Finally, we flip at index 2, flipping all bulbs from index 0 to 2, resulting in the target string 10111. In total, 3 flips are required. Here's another example. If the input target string is 101, we start with all bulbs off, represented by 000. The first flip happens at index 0, flipping all bulbs from index 0 to 0, resulting in 111. The second flip is at index 1, flipping all bulbs from index 0 to 1, which gives 100. Finally, the third flip occurs at index 2, flipping all bulbs from index 0 to 2, and we get the target string 101. Again, the total number of flips required is 3. Now consider the example where the target string is 00000. In this case, all bulbs are already off, matching the initial state. Since no flips are needed to achieve the target, the output is 0. This demonstrates that if the target string consists entirely of 0, no switches need to be flipped. These examples help highlight the importance of understanding the transitions in the target string to minimize the number of flips. Let's also examine some edge cases. First, if all the bulbs are initially off, as in a string like 00000, no flips are necessary, and the output is 0. If all the bulbs need to be turned on, as in 11111, only one flip is needed to achieve the target. For a string with an alternating pattern like 10101, the number of flips corresponds to the number of transitions between 0 and 1 in the string. Lastly, given that the length of target can go up to 10⁵, it's crucial to ensure the solution is efficient and can handle large inputs within these constraints. These considerations will guide the design of an optimal algorithm. To solve the bulb switcher 4 problem, let's start by exploring a brute force approach. The intuition here is to simulate the entire flipping process. Imagine starting with all bulbs turned off, which we represent as zeros. Each time the current state of the bulbs doesn't align with the desired target string, we flip the prefix of bulbs up to the mismatched position. However, this involves iterating through the prefix and flipping bulbs repeatedly, leading to a time complexity of n² for a target string of length n. While this approach is straightforward to understand, it's computationally expensive and becomes impractical for larger strings due to the repeated operations. Instead, we can optimize this process by focusing on the number of state transitions in the target string. The key observation here is that every time the state changes between 0 and 1, or vice versa, a flip is required to align the bulbs with the target. This insight allows us to bypass the need for explicitly flipping prefixes, significantly improving the efficiency of our solution. Now that we understand the key insight, let's break down the optimized algorithm step by step. We begin with all bulbs turned off, which means the initial current_state is 0. As we traverse the target string, we check each bulb against the current_state. Whenever a bulb in the target string differs from the current_state, it indicates a state transition, so we increment our flip count and update the current_state to match the bulb's state in the target. By the time we finish traversing the string, the total flip count gives us the exact number of operations required. This method is efficient because it only involves a single pass through the string, resulting in a time complexity of O(n). The reason this approach works is that it directly aligns with the number of state transitions in the target, eliminating unnecessary computations like flipping entire prefixes. By focusing solely on these transitions, we achieve both clarity and efficiency. When comparing approaches, the differences in efficiency and scalability become clear. The brute force method, while simple to implement, has a time complexity of O(n squared, making it infeasible for larger inputs. On the other hand, the optimized transition-based approach is both direct and efficient, with a time complexity of O(n) and a space complexity of O(1). This means it not only handles larger inputs effectively but also avoids the overhead of redundant operations. As for alternatives, none provide better performance or match the simplicity offered by the transition-based approach within the constraints of this problem. In summary, leveraging the key observation about state transitions allows the optimized approach to stand out as the most efficient and elegant solution to the bulb switcher 4 problem. To solve the problem, we need to determine the minimum number of prefix flips required to transform an initial state of bulbs, where all bulbs are off, to match the target state represented by a string of zeros and ones. A prefix flip means toggling all bulbs up to and including a specific position. We start by initializing a few variables. First, we set the current state of all bulbs to 0, since they're initially off. Then, we use a variable called flip_count to keep track of the number of flips we perform. Additionally, we introduce a Boolean variable called current_parity, which helps us track whether the bulbs have been flipped an even or odd number of times globally. This is important because it allows us to efficiently simulate the flipping process without physically toggling the bulbs. Once these variables are initialized, we iterate through each bulb in the target string, inspecting their states one by one. As we traverse the target string, the next step is to compare the current state of each bulb with the desired state in the target string. To determine the current state of a bulb, we use the current_parity variable. If the parity is even, the bulb's state remains unchanged, matching the initial state of 0. However, if the parity is odd, the bulb's state is flipped to 1. After determining the current state, we compare it with the target state at the same position. If the two states don't match, this means a prefix flip is required at that position. Performing a prefix flip involves incrementing the flip_count by 1 and toggling the current_parity variable to reflect the global flip. This process continues for each bulb position in the target string, ensuring that the number of flips is minimized while transforming the bulbs to match the target state. Let's consider some key insights that make this algorithm efficient. First, instead of physically flipping all the bulbs in a prefix, we use the current_parity variable to simulate the net effect of flips. This eliminates redundant operations and helps achieve an optimal time complexity. Another important insight is that the state of any bulb at a given position depends only on the initial state, which is 0, and the parity of flips applied globally so far. This means we don't need to store or modify the state of each bulb individually. Additionally, if the remaining portion of the target string already matches the current state, we can terminate early since no further flips are needed. In terms of data structures, we only need two variables, current_parity, which tracks the global flip state, and flip_count, which directly answers the problem by counting the number of flips performed. These choices reduce both the time and space complexity of the solution. Analyzing the algorithm's complexity, the time complexity is O(n), where n is the length of the target string. This is because we process each position in the string exactly once. The space complexity is O(1), as we only use a few variables, and the memory usage does not grow with the size of the input. Now, let's consider some edge cases. If the target string consists entirely of zeros, no flips are needed since the initial state already matches the target. If the target is all ones, only one flip is required at the start to turn all bulbs on. For alternating patterns like 010101, the algorithm efficiently handles such cases by flipping only at positions where the target changes. Finally, if the target is empty, no flips are necessary, and this case should be explicitly handled if the input allows empty strings. These considerations ensure the algorithm is robust and handles all possible scenarios effectively. The provided solution solves the problem of determining the minimum number of prefix flips required to transform an initial state of all bulbs, off, to match a given target state. ### line by line explanation. 1. Class definition *. The solution class is defined to encapsulate the solution to the problem. LeetCode requires solutions to be implemented within a class structure. 2. Function definition *. The min-flips function is defined, taking target, a string representing the desired bulb states, as input. This function computes and returns the minimum number of prefix flips needed. 3. Initialize variables *. Flips is initialized to 0. This variable will count the number of flips performed. Current_state is initialized to 0, representing the initial state of all bulbs being off. For iterate over target *, a for loop iterates through each bulb state in the target string. 5. Check for state mismatch * inside the loop. It checks if the current bulb state in the target string, bulb, is different from the current state of the bulbs. If there is a mismatch, it means a flip is needed to toggle all bulbs up to this position, so flips is incremented by 1. The current_state is updated to match the value of the current bulb. This ensures subsequent comparisons are made against the updated state. 6. Return result * after processing all bulbs in the target string, the total number of flips is returned as the result. ### intuition. The key observation is that a flip is only required when the desired state of a bulb differs from the current state. Each flip ensures that all bulbs up to the current position match the desired state. By counting such mismatches, we determine the minimum number of flips needed. ### edge case handling. If the target string contains all zeros, no flips are needed, and the function correctly returns 0. If the target string contains alternating zeros and ones, the function calculates the correct number of flips by counting transitions between 0 and 1. ### complexity analysis. Time complexity *O, n, where n is the length of the target string. The function iterates through the string once. Space complexity *O, 1, as the solution uses a constant amount of extra space. This is the Java implementation of LeetCode problem number 1529, bulb switcher 4. The logic mirrors the Python solution, where the number of flips is calculated by iterating through the target string and counting transitions between states. Key differences include Java's explicit type declarations and the use of char arrays for string iteration. The algorithm runs in O, n, time, where n is the length of the target string. In this problem, we're tasked with determining the minimum number of flips needed to convert a sequence of bulbs, which all start in the off state, into a given target configuration. Flipping a bulb toggles not only the state of that bulb but also all the bulbs that come after it. To solve this, we can leverage a key observation: a flip is only required when the state of the current bulb differs from the state of the previous bulb. By iterating through the target string and tracking these state changes, we can efficiently count the number of flips required. For instance, if the target is 101, we start with all bulbs in the off state, which we can represent as 000. From here, we'll calculate the flips step by step to reach the desired configuration. To solve the first example where the target is 101, we initialize two variables, flips to 0 and current_state to 0, representing the initial state of all bulbs. We then compare each bulb in the target with current_state. For the first bulb, the target is 1, which is different from current_state. This means we need to flip the first bulb, bringing current_state to 1 and incrementing flips to 1. Next, we compare the second bulb in the target, which is 0. Since it doesn't match current_state, we flip again, updating current_state to 0 and flips to 2. Finally, the third bulb in the target is 1, which again differs from current_state, so we flip once more, setting current_state to 1 and increasing flips to 3. At the end of this process, we've successfully transformed 000 into 101 using 3 flips. For the second example, where the target is 000, no flips are needed since the bulbs already match the target state. We verify this by iterating through the target, comparing each bulb to current_state, and finding no mismatches. In the third example, the target is 111, and we again start with flips set to 0 and current_state is 0. The first bulb in the target is 1, which differs from current_state, so we flip the first bulb, updating current_state to 1 and setting flips to 1. For the second bulb, the target is still 1, which matches current_state, so no additional flip is needed. Similarly, the third bulb also matches current_state, so no flip is performed. This brings us to the final state 111, achieved with just one flip. From these examples, we can make some important observations. First, a flip is only necessary when the current bulb state differs from current_state. Second, the algorithm achieves optimal efficiency with a time complexity of O(n), as we only need a single pass through the target string. Finally, edge cases like all zeros require no flips, while all ones require just one. To summarize, the number of flips required for each example is as follows. For the target 101, we need 3 flips, for 000, no flips are required, and for 111, only one flip is needed. This algorithm is both efficient and correct because it carefully tracks state transitions and counts flips only when necessary. By iterating through the target string and updating the state whenever a mismatch is found, we ensure that the solution is optimal and easy to implement. In this problem, the time complexity of our solution is O(n), where n represents the length of the input string, target. This is because the algorithm processes each character in the string exactly once using a simple for loop. Within each iteration, it performs a constant time comparison between the current bulb state and the current_state variable. If these states differ, the algorithm increments the flips counter and updates the current_state, both of which are O(1) operations. Since there are n characters in the string, and each character is handled in constant time, the overall time complexity is O(n). Whether in the best case, where the target consists entirely of zeros, or in the worst case, where the string alternates between 0 and 1, the algorithm still processes all characters once. This consistency across all cases ensures an O(n) time complexity. Thus, the time complexity remains O(n) regardless of the input. Now, in terms of space complexity, the solution is highly efficient, requiring only O(1) space. This is because the algorithm uses just 2 variables, flips, an integer counter, and current_state, which stores a single character, 0 or 1. These variables occupy a constant amount of memory, regardless of the size of the input string. Furthermore, the algorithm does not rely on any additional data structures, such as arrays or lists, nor does it use recursion, which could increase memory usage. Since the input string target is part of the input itself, its memory is not included in this analysis. Therefore, the space complexity remains O(1) at all times. To put this into perspective, let's compare the optimized approach with a naive solution. A brute force method might involve flipping each bulb individually while directly simulating the process for every bulb. This could result in additional operations proportional to the number of flips, leading to a worst-case time complexity of O(n squared). Moreover, such an approach might require storing and updating the state of all bulbs in memory, which would increase the space complexity to O(n). In contrast, the optimized solution avoids unnecessary simulations by simply tracking the required state changes. This allows the algorithm to achieve an O(n) time complexity while maintaining an O(1) space complexity. The mathematical justification for this is straightforward. The number of iterations is directly proportional to the input size, and all operations within each iteration are constant time. Similarly, the space used remains fixed, independent of the input size. This efficiency makes the optimized approach far superior to the brute force method. In this section, we're addressing some common mistakes that can occur when solving the bulb switcher 4 problem. First, it's important to account for flipping propagation. When you flip a prefix, it doesn't just impact one bulb, it alters the state of all bulbs within that range. Missing this detail can lead to incorrect state updates and mismatches with the target string. Next, overcomplicating the flipping logic is another frequent issue. Instead of manually tracking the flipped state of each bulb, it's better to rely on the current state and the target string directly. Overthinking this can unnecessarily inflate complexity and make your solution more error-prone. Another pitfall is using nested loops inappropriately. For example, iterating over both the prefix flips and the bulbs within each flip results in an O(n squared) solution. This approach quickly becomes inefficient for larger inputs and can exceed time limits in competitive coding environments. Finally, there's a common misinterpretation of the initial state. The problem assumes all bulbs start in the off position, or 0. If you assume otherwise, you might miscalculate the number of prefix flips required to match the target configuration. Neglecting edge cases is another mistake that can lead to incomplete solutions. For instance, failing to test scenarios like a target string of all zeros, all ones, or alternating patterns may leave your solution untested for critical inputs. When approaching this problem, a key insight is that the number of flips corresponds to the number of transitions between 0 and 1 in the target string. This observation simplifies the solution to linear time complexity, (O(n), as opposed to a brute force approach. In problems involving prefix operations or cascading effects, it's often helpful to focus on observation-based solutions rather than directly simulating every step. Additionally, during an interview, make sure to clearly explain how flipping a prefix impacts the subsequent bulbs. Communicating the cascading effects effectively can make a strong impression. Lastly, if you optimize your solution by reducing the complexity from O(n)² to O(n), highlight that during the interview. This demonstrates your ability to identify inefficiencies and implement improvements. Now let's look at related problems and alternative approaches that can help reinforce the concepts in Bulb Switcher 4. One closely related problem is LeetCode 1375, number of times binary string is prefix aligned. This problem also focuses on operations involving prefixes, making it a great practice for similar logic. Another valuable problem to consider is LeetCode 1288, remove covered intervals. While it's not directly related to flipping bulbs, it emphasizes observation-based optimization, which is a transferable skill. Lastly, LeetCode 189, rotate array, involves cumulative changes applied iteratively, and though conceptually different, it shares some similarities in how states evolve over multiple steps. As for alternative approaches, a brute force solution explicitly simulates each prefix flip. While this method is straightforward to implement, it's highly inefficient at O(n)² complexity. On the other hand, a more optimized approach involves counting transitions between 0 and 1 in the target string. This method is efficient, with O(n) complexity, but it requires deeper upfront observation to identify the pattern. Another powerful strategy is the greedy approach, which simplifies the problem by focusing solely on mismatches between the current state and the target. With this method, you flip the prefix only when you encounter a mismatch. This approach is as efficient as transition counting, with O(n) complexity, but it emphasizes state updates rather than directly counting transitions. Both methods achieve the same result but approach the problem from slightly different angles. The key takeaway is to prioritize simplicity and efficiency in your solution. Whether through careful observation of transitions or by employing a greedy strategy, the goal is to reduce redundant computations while maintaining clarity in your logic. This ensures your solution is not only correct but also optimal and easy to explain in an interview setting. Great job! We've successfully solved the problem by leveraging an efficient approach. Remember to focus on the state changes in prefix problems. Thank you for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!